We are running our latest AI tools on hardware built for a defunct era. The dominant general-purpose graphics processing units, GPUs, were conceived years before anyone seriously suggested serving AI to a billion people at once. For the last few years, the focus was almost entirely on training, running massive server clusters for months to teach models how to think. But the vast majority of computing work has now shifted to inference, the actual day-to-day process of models answering prompts and generating text. Right now, only a tiny fraction of the planet actively uses these tools. We are moving toward a baseline where hundreds of millions of autonomous AI agents will be running concurrently, around the clock, consuming data at speeds no human could ever match. That specific workload, massive continuous inference, now dictates the market. Because general-purpose chips are highly inefficient at handling it, the entire hardware stack has to be rebuilt from the transistor up. As the workload changes, the industry metric for success is moving away from raw computing speed. This illustrates how performance is measured now. We've shifted from a standard speed dial to an energy efficiency gauge. The critical question today is throughput at a fixed level of interactivity. We measure success strictly in terms of tokens per watt or agents per megawatt. Taking general-purpose silicon and trying to retrofit it for these new energy constraints simply doesn't yield the math we need. To hit those targets, hardware has to be engineered specifically and exclusively for inference. To understand how you build that specialized silicon, we have to zoom all the way down to the microscopic level. The very first barrier engineers hit is basic thermal physics. Look at this power curve. As you pack more processing units into a single chip, the power draw rises exponentially with the voltage. This physical law, known as Dennard scaling, means a chip will literally cook itself if it doesn't throttle its own clock speed to manage the heat. To flatten out that steep power curve, the next generation of inference hardware runs on ultra-low voltage silicon. By dramatically dropping the power consumption, engineers can afford to pack in vastly more operations without melting the hardware. Once you solve the heat, you hit a second physical wall, memory latency. Moving data from one chip to another currently takes on the order of 4,000 nanoseconds. When your entire process relies on shuffling a model's memory around, a 4,000 nanosecond delay is a massive bottleneck. By building near speed-of-light interconnects between processors, you eliminate that gap. You stop treating a server rack as thousands of individual chips talking to one another and start treating an entire scale-up cluster as one single highly unified memory pool. Specializing for a single workload also means you can throw out decades of general-purpose assumptions. Standard design tools assume a microchip might need to operate in 0-degree weather. AI data centers never drop to freezing, and stripping out that requirement alone opens up a cascade of technical optimizations. Push that hyper-specialization to its limit, and you get disaggregation. This is the process of splitting AI inference into two entirely distinct physical pipelines, rather than forcing one chip to do everything. Look at how this server rack divides the workload. On the left side, we have the prefill stage. This is where the AI reads in your initial prompt and gets its memory into the right state. It's an incredibly compute-heavy task, so it runs on processors built specifically to churn through dense blocks of incoming data. Over on the right side is the decode stage. This is the token-by-token generation of the actual answer. Decode is a memory-bound process. It needs immense bandwidth to output thousands of thin, fast streams of data. Putting both of those stages on the same chip is a compromise. The future data center acts like a highly tuned assembly line, passing the data through a series of distinct processors that only perform the exact job they were born to do. But betting billions of dollars on highly specific hardware carries a massive financial risk: architecture lock-in. Almost all of these new specialized chips are etched specifically for the transformer architecture, the software model that powers today's major AIs. If a more efficient software architecture replaces the transformer tomorrow, all of that expensive, single-purpose silicon instantly becomes obsolete. General-purpose GPUs have a distinct insurance policy. They can run whatever comes next. The current market leader holds a massive, deeply entrenched software ecosystem that developers already know how to use. New competitors have to convince customers to abandon a familiar, flexible toolchain for a rigid one. If these technical and adoption hurdles are cleared, the hardware evolution moves from the server rack up to the building level. We arrive at the ultimate endpoint, the token factory. Right now, we essentially generate AI tokens by hand, using general-purpose machines with no real economies of scale. We are moving towards single, monolithic manufacturing facilities, $100 billion and eventually trillion-dollar campuses that run at gigawatt scale. A smartphone doesn't get exponentially better just because you're a billionaire. Mass manufacturing collapsed the cost and flattened the quality curve for everyone. These mega facilities will apply those exact same unit economics of physical commodities to the mass production of machine thought. In a market driven by mass production, raw availability beats clever engineering. The companies that dominate will not be the ones with the smartest chip design, but the ones capable of manufacturing token capacity by the gigawatt. If token production asymptotes toward becoming a majority of global economic output, the supply chain behind it becomes the most strategically sensitive choke point on Earth. As this global map shows, resources required to sustain this industry are severely restricted. Power will consolidate into the hands of the few entities that control the leading-edge fabrication plants, high-bandwidth memory suppliers, and the massive energy grids required to keep the lights on. A society that relies entirely on 2 or 3 monopolized megafactories for its intelligence is highly efficient, and it is incredibly fragile. The necessary counterweight to that consolidation is a local-first, open-weight ecosystem. This is the practice of ensuring everyday people and small organizations can run highly capable models locally on hardware they actually own and control. The massive economies of scale will inevitably pull towards centralized factories. Ensuring that machine intelligence remains a widely distributed, locally accessible capability is how we maintain independence in an automated age.